Okay, so here's a different way to find some of these things, and at least this isn't going to prove that there can't be other ones, but luckily we already did that. But we can use continued fractions and logarithms. You've not seen logarithms?
Yep.
You have a little bit, right?
Yeah.
We can use continued fractions and logarithms to find other powers that are close. So I'm going to define a number a here to be log base 10 of 3 divided by log base 10 of 2, and then I'm going to start looking at continued fractions of that number. The first, with two terms, I get just the number 2. And if I do 2 squared and 3 to the 1, I get 4 and 3, and I get a difference of 1, and difference is 1/3 of the smaller number. Okay.
Yeah.
So even though they differ by 1, they're sort of still far apart. 1's kind of a big number compared to 3 and 4. You see what I'm saying?
Yeah.
If I do the 3 terms, now I get 2 cubed and 3 to the 1.
Yep.
3 squared.
Yeah, sorry, I confused myself for a second. Okay, so now I get 8 and 9, and I get a difference of -1.
Yep.
Which is still more than 10% of the power of 3. Sorry, I said smaller number before, but I just mean the power of 3. But it's actually a better approximation than we got before, even though it differs by 1, but it's somehow closer. If I go 4 terms out in this, I get the fraction 8/5. So 2 to the 8 and 3 to the 5th. Now they don't differ by 1 anymore. In fact,
But
they differ
it's
by...
close.
Is that less
13.
on the screen there?
The 243 is that number, isn't it?
Okay, so let me just zoom out a little bit. Okay. Now they're only 5% apart. So even though they don't differ by 1, it's a slightly better approximation.
Yeah.
Even though they're getting farther apart, it's still closer compared to the numbers. Now I'm going to go 5 terms.
19.
2 to the 19
And 3 to the 12th.
and 3 to the 12th.
Now it's getting there.
Now the number is 531,441 for 3 to the 12th and 524,288 for 2 to the
They're
19th.
reasonably close.
Seem like they're getting far apart, but as a percentage, they're actually getting closer. They're only 1.3% apart. If I go 6 and I get
65.
2 to the 65th and 3 to the 41. Whoa, what happened there? 3 to the 41.
This is 0.11.
So you see, now we're getting into gigantic numbers. But
But
they're only,
there's-
now last time it was 1.3% apart, now they're 1.1% apart. But you can see that they're starting to differ by huge amounts.
Like
Yeah.
this is off by, it's like 4, about 4 quintillion.
Yeah. But it's still only approximately 1% of the difference between the numbers.
Yeah.
Okay, and this will be the last one we do. We'll go 7 terms out in the continued fraction. 2 to the 84 minus 3 to the 53rd.
This is 0.0.
0.002. So I'm
0.2% apart.
you're right, 0.2% apart. So these numbers are super close together compared to how big they are.
Yeah.
But the problem is they're just enormous, right? So this is millions, billions, trillion, quadrillion, quintillion, sextillion, septillion, 19 septillion.
Yeah.
So they're huge.
Yeah.
So you can see that the powers are growing very fast. There are some numbers that are reasonably close together, you would say, but we're not finding any that differ by 1.
Yeah.
You know what I mean? You want us to just see how big the numbers get for the next one? Uh-oh.
45 over.
485. 2 to the 485 minus 3 to the 306. Uh-oh.
Wow.
But they're 0.001% apart.
Yeah. So that's the next pair that's close. And you can see how close they are. It's 1 part in 1,000,
Yeah.
different from each other. It's just the numbers are slightly bigger than 1,000,
Yeah.
one might say. In fact, are they so big they don't even fit on the screen? Yeah, it doesn't even matter. The numbers are just gigantic.
Yep.
Anyway, so cool problem, right? So
Yep.
we solved this using just basic ideas from number theory and factoring polynomials.
Nice.
Pretty cool. All right, good work, guys. High five.